Well, scoring a sequence alignment. So how do we judge the quality of an alignment? Well, we need a scoring system of some sort, and the system usually penalizes for poorly aligned or poorly matched amino acid alignments, and the positions that have identical matches or closely related residues, those ones are given a more favorable scores. So using the sequence 1 and sequence 2 above as an example of an alignment between the two sequences, you see how the scores were generated. The total score is 26, and it came from the individual scores at the various positions. Obviously, these actual individual scores are not just randomly picked. They come from an actual compilation that's called an amino acid substitution matrix. There you have tables of compilation that have these various scores for aligning, say, a valine with a valine or a cysteine with a cysteine, and then those scores are the ones that are added up, and then the algorithm is able to calculate the total match or the total score for your alignment. It's important to note a few things with alignment. One is that non-identical amino acids can be placed in corresponding positions, but as you can see here, they'll result in a slightly lower scores than if it was an exact match. Also, look at the matches themselves. Even though they're matches, they all don't score the same. For example, this valine and valine, it's scoring a 4. Aligning a serine and serine also gives you a 4, but aligning a cysteine and another cysteine, that gives you a 9. So therefore, this goes to tell you that in those substitution matrices, we compare and consider the nature of the amino acids that have been matched. So those that are rare, when they're matched together, we get a higher score, whereas the more common ones will score a little bit less. Also look at the situation where you have to introduce a gap, and look at the score for the gap. It's -11. So gaps are very much heavily penalized, and this is because in nature we don't think they just happen all the time. So if they have to be included, it has to be only if necessary, and that's only to improve the score of your final alignment. So gaps, when necessary, they can be introduced to improve your global alignment. In this example, it's very easy to see which positions warrant gaps to make the alignment score be optimal, obviously because it's short. But if it were a larger alignment, much longer, involving much longer sequences, then it will be very difficult to do this by eye. And that's where the dynamic programming comes in to help rescue the situation, because it can readily place for you the gaps where they need to be, so that the output that you get is the highest possible scoring alignment that you can get. So what does dynamic programming algorithm exactly do? So as an example, let's walk through the steps or procedures for the dynamic programming algorithm. Here the emphasis is more on the principles or concepts rather than the actual math here. So consider aligning sequence on top in the top left of this panel with a sequence at the bottom, and having that as your ultimately best scoring alignment, coming with a score of 15. We'll call that the optimal alignment that can be attained between these two sequences. Now consider that alignment, which is optimal, initially started by aligning the initial amino acid pair that started with a VV, and then building the alignment sequentially, step by step at every position after that. So that really means that this optimal alignment at the top left must have come from another previous alignment, which was A, which itself was also optimal at that stage before the final amino acid pair YY was added to result in the ultimate optimal entire global alignment that we said is the highest scoring. It gave us the score of 15. Also, extending the same logic, you can say that alignment A itself must have come from a previous alignment which also similarly was also optimal at that step before a CC pair was added to result in the suboptimal alignment A, which is optimal at up to that stage, which also resulted in the optimal alignment 1, which we are saying as the best scoring alignment for the global alignment of our sequence. What this really tells us is that our alignment can be traced back sequentially to the first aligned pair, which itself must also have been optimal. And to conclude, what this shows us is that using the dynamic programming algorithm, one can build an optimal alignment stepwise, starting with a smaller sub-alignment that is of optimal and adding on residue. As long as every increment results in an optimal alignment or an optimal score up to that position, you can end up having an optimal alignment for the entire sequence length, which is produced stepwise. How about gaps? Well, we say that gaps are inevitable in alignments. It's virtually almost impossible to produce a really global alignment for long sequences without having to factor in some gaps in one or even both sequences. But we also say that gaps draw up a huge cost because they don't come really free. So for that, you have to think of an opening penalty that introduces your gap. So this will define the cost for opening a gap in one of your sequences. There's no simple rule to predict the optimal value to assign such a gap penalty, but you just have to remember that if it's much higher than the default in your computer program, then local alignment that contain gaps may be split into shorter alignments. Also, you can have gap extension penalty that will factor in the proportion of the length of the gaps that has been introduced. But this one usually is much lower than the gap opening penalty, to the tune of maybe a tenth less. So that's a good ratio or good range to judge your gap opening and gap extension values. Obviously, the whole point of the gap opening and gap extension proportions is that gaps should be penalized more on their existence than their actual length. So when you're faced with a situation and you want to do a global alignment that involves, say, comparison of distantly related sequences, it's good to go for a high gap score and a really low gap extension score. What about the algorithms themselves? We said for the global alignment, that is to align the entire length of your sequences, you go with the Needleman-Wunsch algorithm. This was derived from the dynamic programming method, and it was first used in 1970. So to get an optimal score for the alignment from this, you have to add up the sum of all the positions, and you have to subtract the gaps where they would have occurred. And in that substitution matrix that's used by the Needleman-Wunsch algorithm, the scores themselves for the pairings can be positive or negative or even 0. Okay. Remember that this Needleman-Wunsch algorithm was designed really to maximize the number of matches between the sequences along their entire length. So to produce a global sequence alignment from this scoring matrix, you need a second matrix called a traceback matrix. Remember, you can't do all these comparisons in a very long sequence all at once. So you have to break up the positions into smaller problems, which you have to ensure that they have the optimal scores themselves. So to keep track of the trial moves that one has to go through, a second matrix called the traceback matrix usually is produced. And that then guides the path when you get to stringing back together the suboptimal solutions, that the suboptimal, the part of the optimal solutions that contribute to the final optimal solutions. So there's the traceback metrics are used to keep track of all those various sub-problems that you have to solve in order to arrive at your final optimal solution. So like everything else, this algorithm has advantages and disadvantages. it's really well suited to do global alignment, like I've said, but of two closely related sequences. The downside is that it can miss best local similarity because it's not designed for, local similarities. It's also unsuitable for aligning very divergent sequences. It will struggle in that respect. And sequences that have different domain structures interspersed with other regions that are not matching so well, the global alignment will struggle with those. Well, the other alignment option is the local alignment. And for this, we have the Smith-Waterman algorithm. It too was a modification of the dynamic programming algorithm, but this came a bit later in 1981. And the rules for calculating the scoring matrix varies slightly from the ones we saw with the Needleman-Wunsch algorithm. The main difference here is that the scoring system for this includes negative score for mismatches, but what happens to them is that during the processing, that negative score is automatically set and it's made to be a 0. And what this ends up doing is it terminates the alignment up to that point so that a new one can begin. Here you also have the traceback matrix, just like in the other algorithm, which helps you keep track of all the trial moves that you have to make. And here the alignment that's produced is the highest scoring one, whereby you started at the highest scoring position in the matrix, following your path up to the point where you reach 0. The Smith-Waterman algorithm also has advantages and disadvantages. It's very useful in alignments where the global alignment will not be very helpful there. And that's because you may be wanting to identify conserved local sequence domains which are present in both sequences, and you know that the global will not be a good tool to help you with those. And you may be intending to match sequences that happen to have different lengths of overlap. And here the Smith-Waterman can come in better. So it has disadvantages, like I said. One of its advantages is that it struggles finding the highest scoring alignment when sequences include regions that align locally well, separated by intervening regions that are aligning really poorly. For that, it will struggle there.